So take it away, Pete.
Where am I bringing it to? All right, so how can I trust anything? Transfer functions, calibration, and the art of uncertainty. Yeah, like I said, who is this guy? You guys know me, but then again, not all of you know my background. So originally I was trained as a physicist. Right out of school, I got a job for a year and a half, getting injured on the job almost by problems that my boss would throw at me as a calibration technician in the field. Then I did software QA, QC, high five, Sarah, and also acted as an IT technician for a small company, high five, Jacob, too. Then I was an instrumentation builder and audio recorder / acoustic device engineer. And then the rest of this stuff, yeah, self-employed nut job. That was what I had right before I started working here. So I'm still doing that on the side. Anyway, we've got a couple of key terms that we're going to be going through today. So it's vocabulary time. I'm going to be upfront with you. Unfortunately, I believe most of you will be disappointed by the number of plots and charts and graphs in this slideshow. But you may be also surprised at the number of equations and how simple they are to understand, hopefully, if I do my job right. So we're going to start out with just listing these: sensor, actuator, transducer, measurand, transfer function, sensitivity, resolution, uncertainty, characterization, adjustment, calibration, and traceability. And don't worry, there won't be a quiz. So starting out with sensor, actuator, transducer, these are the parts that actually interface with the real world. A sensor is a device that transduces a physical phenomenon in the world into some sort of signal. In our case, that's usually electrical. An actuator then is a device that does the exact opposite. It transduces a signal into a physical phenomenon. Usually we don't use these, but if you wanted to influence something, like, for example, have sound coming out of a speaker is an actuator. Takes an electrical signal in and then turns that into a physical quantity in the real world. And then a transducer is simply a device that transforms one form of energy into another, like, for example, temperature to electricity, or back again. A measurand now is the physical thing, the object or phenomenon that's being measured. A transfer function then is a mathematical description of the behavior of a transducer. And its sensitivity is the relationship between the input and output sides of a transducer. We'll get into a little bit more detail on that in a little bit. Resolution is how fine of a measurement can be made by a given measuring device. So for example, if I have a thermometer and it only goes down to 0.1 degrees C, then 0.1 degrees C is my resolution. Uncertainty then is a range of values where the true value of a measurement might lie with some probability. On that same thermometer, if I have a resolution of 0.1 degrees C, usually my actual uncertainty will be plus or minus let's say 2 or 0.3. So it could be, the real measurement could be anywhere within that value of what we're seeing on the display. Then we've got characterization, adjustment, calibration, and traceability. Characterization is the act of experimentally determining the transfer function of a given instrument or transducer. Sarah has been characterizing the behavior of dissolved oxygen probes, and the behavior has not been necessarily the greatest, so we work on that. Adjustment is the tuning of an instrument so that its output is in line with reality. When you put the two of these together, then you get calibration. Calibration can't exist without adjustment. Without adjustment, calibration is just characterization. So you do have what's known as kind of a zeroth order calibration where you don't have to make an adjustment. So if I take like a gauge pin, something that's supposed to be exactly 1 millimeter in diameter, I measure it with micrometer and it turns out to be 1.00000 millimeters, then I don't need to adjust anything. I don't have to file it. I don't have to like readjust the micrometer if that's the thing that I'm calibrating. The adjustment part is a zero adjustment, but there's still the option to adjust, which means that even though I've only characterized the relationship between the gauge pin and the micrometer, there's still a calibration that's occurred. It's just that the adjustment is 0. So the calibration then is a cycle though, because usually you need at least 3 steps. You need to characterize, then you need to adjust, and then you need to characterize again. Then you need to know if, then from that, you know whether you need to adjust yet again. So it's a dance. You're going back, you're going forward and then backward and then forward and then backward, and now we're cha-chaing, or in this case, calibrating. You're welcome, Jacob. You get a real genius quote.
Thank you.
So traceability is the use of generations of more precise devices to calibrate less precise devices stemming from an initial single source. I had this, in retrospect, I dare say, really great lab that I used to do with some of my students. We'd get a stack of plastic tubes or rods, and I'd have them measure the first one and cut it at exactly 10 centimeters. And then what I would have them do is on the rest of the rods, they would have to use that first rod as the ruler. And then the second rod becomes the ruler for the third. The third rod becomes the ruler for the fourth, all the way on down. And then we'd take a very precise pair of calipers and we'd measure each one of those different rod lengths and see if they trended in a particular direction, because they were never exactly the same. And they were definitely not the same as the ruler. So what we usually found was across the entire class, we'd get a bimodal distribution where you'd have the people whose rods happened to trend upwards in length, and those were in this particular part of the distribution. And then they had the other students whose rods trended downward in length. They cut low rather than high. And we had almost nobody in the middle, where you actually would have the real measurement of 10 centimeters. So we usually got like our bimodal distribution was centered around like, I think it was 10.75 and like 9.25 centimeters. So it was definitely obvious to even the casual observer that 10 centimeters was not 10 centimeters by the time you got 10 generations out. And that's exactly traceability. This is a matter of bringing the measurement that we know is true through a number of different noisy systems, or in this case, a number of different measurements and other cyclical references out to the eventual measurement that we're making. So getting back to a transfer function. What is in a transfer function? We start, in this case, on the left side here. We have a measurand, a thing in the real world, in real life, that is making some particular signal that is expressed mathematically as S of t. So S of t is how much that particular signal is at some given time t. So if I have a FieldKit, for example, and I'm measuring, once again, let's go with temperature because it's simple to think about. I'm measuring a pot of water as it's on, my apologies, Susan, it's on the hob, getting ready to boil, because I want to make myself a cup of tea or coffee. And I have the temperature sensor in there. That means that as the temperature, or as time passes, the temperature is also going to be going up. So what I want to know eventually is, on a computer somewhere, I need to store this data. But in the real world, I just have temperature and time. So in our case, the signal is just the temperature. And then the time that it takes for the pot to boil, that's almost immaterial. It's just that at given points in time, we take a temperature. And then we can start looking at those temperatures and seeing a curve emerge as we see the heating occurring. The thing is, though, that the measurand in this case is just the temperature of the water. But the water then is conveying temperature through, in our case, a stainless steel jacket, some, I think it's silicone room temperature vulcanizing rubber, and then into that tiny piece of platinum in the middle of the thermistor, the actual temperature sensor. So the medium in this case is the steel, the rubber, and also the area of the water that's actually around the sensor. Now we get into the transducer itself. Now we get into that tiny little piece of platinum. And you see that the transfer functions are starting to nest outwards. We're multiplying by a different transfer function every time. So we start off with just the real temperature at a given time. Then we start seeing, okay, well, the temperature has to be plus or minus some amount because of it going through this medium that's going to lag in its temperature change relative to the water around it. And then from there, we lag even further into the transducer, but the transducer is where the magic happens. That's where we turn from temperature into, in this case, resistance. Then that resistance itself is acted upon by the fact that it has to go through a transmission line. And this is the part that's probably going to give Bradley nightmares because this is analog design stuff. The transmission line is really just a cable. In our case, it's a piece of coaxial cable that sits between an SMA connector and our actual thermistor, the little piece of platinum in the temperature sensor. And that has a certain length to it and therefore a certain amount of resistance. And it does a certain deterministic thing to the signal that's coming through it. So now we're at this other n of y of m of s of t function. And finally, we have the front end. In our case, we have almost no front end. We just have a voltage divider. And technically speaking, the voltage divider has a nonlinear relationship with temperature, but it's small enough that we can model it as being temperature is directly proportional to voltage. Finally, that goes into the analog to digital converter. And now we change completely the way that we're looking at the signal. Up to this point, everything has been continuous over time as a continuous variable. Now we're in the D of n space, and we're moving from being a continuous time curve to instead being discrete time measurements, where we actually take a particular value at a particular moment. And so our sampling frequency or our sampling rate, or the period between different samples, let's say that it's once every 10 minutes, which is one of our default settings kind of, then that means that every 10 minutes, I take this digital number off of the analog to digital converter that then reflects all of the analog stuff that came before it, the front end, the transmission line, the transducer, the medium, and the measure end. So this is a signal chain. Actually, this is a relatively simple and uncomplicated signal chain, which is kind of terrifying, but there's the math. So what's inside of that transfer function? So in our case, resistance and temperature that's the relationship we're looking for. Resistance itself is a function. Notice the T here is different. This is big T. Big T is temperature, little t is time. Resistance as a function of temperature is equal to the resistivity times the thermal expansion divided by what's known as thermal necking, or basically the amount that something spreads out. So I wish I had gotten some sort of plastic or something that was stretchy here and I could show it. Oh, well, I actually do have something like that. I don't know how large my my view is going to be for my face and such, but if I have a piece of plastic here and I pull on it, then this necks as I pull on it. You see how it's decreasing in width, and it's also going to be decreasing in thickness over here, but it's increasing in length. So that occurs every time that you heat something up as well. Once it starts expanding on the length dimension, because you have a finite amount of mass and the density is not changing all that quickly, you also get a decrease in cross-sectional area. So because of that, this third variable comes in, this thermal necking variable. So resistance then is going to be resistivity times length divided by area. And resistivity is basically, it's just how resistive the thing is per unit length, technically speaking. But in this case, we also have length over area. So that's the other length unit that we need to get rid of. So then the rest of the transfer function for us is dependent on a voltage divider. And well, we've got relatively few people with cameras on, so I can't ask you to raise your hand if you've seen this before, but I think most of us have. If we're looking at a voltage divider, we're looking at two resistors, and one of them is going to be, in this case, our upper one is our temperature dependent resistor, our thermistor. And so as that resistance increases, then we're essentially taking that midpoint, the voltage out. As RT increases, we're moving it further down towards ground. As RT decreases, we're moving it further up towards the positive voltage on here. So we wind up with these two expressions. We start out with just the voltage divider equation, V out equals V in times RB over RB plus RT. But then we expand that, because remember in the previous slide, R of T is its own function. So we can substitute in for that with this whole mess. It's a mess, but it's a deterministic mess. It's something that we can characterize, and therefore something that we can predict in the future. So now we go to the next step in the transfer function. We're going to go to the D of n space, where we go to discrete digital numbers rather than being in the continuum space of analog measurements. And the digital out, or the nth element in a string or a stream in least significant bits, is going to be equal to V in, which in this case, that we're taking this segment from the voltage divider where we have V out here. That's going to be V in the next stage. So we multiply that V in by 2 to the something, whatever bit depth we have. Now in our case, we have a bit depth of 24 bits. And then so that means that we have 24, we have 2 to the 24th possible values that we can actually measure. In reality, it's a little bit less. It's closer to 2 to the 22nd because of the fact that we have noise at the very lowest levels. But so that gets into bit depth versus effective bit depth, but that's going too far down the rabbit hole. We'll come back about a meter. So if we divide that by the reference voltage that we're comparing this to, which in our case is 2.048 volts usually, then we know how many individual bits we have, how many least significant bits we're counting for a given voltage. So I just multiply them? Yeah, it's actually that simple, although this doesn't really look simple. But what we're going to do is we're going to work our way through this from left to right. So left is what we're going to get out of this. D of n, the actual digital number that we see from our analog to digital converter. It's equal to VCC, which is that, or sorry, I say VCC here, I should say VREF, but the reference voltage that we're working with, multiplied by the bias resistor that we saw before, RB, divided by bias resistor plus the resistance of the thermistor, the actual temperature measurement probe. And that whole thing is basically how resistive this thing is at a particular temperature times its length at a particular temperature divided by its cross-sectional area at that temperature, all of which change continuously. And then we multiply that whole mess by how many bits we've got to work from divided by how many volts they span across. So let's go back for a moment here to a much simpler system. With an Arduino, for example, I have 1,024 possible values on its analog to digital converter. That's 2 to the 10th. Usually it's referenced to either 5 volts or 3.3. 5 makes the math relatively easy. So you get about, I think it's 4.8 millivolts for every single one of those least significant bits. For us, we're down in like the microvolt range. So it's way, way the heck smaller for a 24-bit ADC. And that's nice for us because it means that we can deal with much smaller signals and still actually see them. But for the Arduino, the math is a little bit more human scale. I, to be completely honest, still have not gotten my brain to immediately recall what 2 to the 24th is. If somebody else has, please jump in.
16,777,216.
Thank you. Well, that is what a 24-bit number has in it. That's how many bits, that's how many least significant bits wide we have.
It's also the number of unique colors because of 24-bit color. So you get
whereas Apple used to call it millions, right? What was it? Millions of colors, thousands of colors, billions of colors. All right, so now we go into everybody's favorite dimensional analysis time. Does anybody remember this stuff? The dimensional analysis, the whole, I'm going to write things out as a bunch of fractions and then I'm going to put slashes through them.
Yep.
Please don't tell me I was the only one who had fun putting the slashes through the units.
It feels like going down a checklist, I guess.
Yeah, it does. It really does. And you're checking every time to say, oh yeah, I got that right. So in our case, the analog to digital converter has a sensitivity in least significant bits per volt. The voltage divider has a sensitivity of volts per ohm. The thermistor has a sensitivity of ohms per degree C. We multiply all three of those and we can check our work from this mess and instead look and say, yes, we have least significant bits per degree C. This is a sensitivity that I can actually use because I get a number in from, in our case, a module board and the analog to digital converter on it. And then I can say, multiply that by this particular number and I get out a temperature. So my measurand has made it all the way from one side of, or my measured quantity has become from a measurand an actual number that sits inside of digital storage or memory somewhere that I can then analyze later. So what about a big signal chain? Well, that's actually perfect cue because it's time for a game of telephone. I'm going to stop share for a moment so that I can put the audio on.
What? Oh, that, no.
There we go. Let me make certain I have this up. All right. Desktop 2, there you are. One moment, please. All right. Tell me if you can see and hear this. Oh, when it decides it wants to start playing.
One hen, 2 ducks, 3 squawking geese, 4 Limerick oysters, 5 corpulent porpoises, 6 pair of Donnell Verzo's tweezers, 7,000 Macedonians in full battle array, 8 brass monkeys from the ancient sacred crypts of Egypt, 9 apathetic, sympathetic, diabetic old men on roller skates with a marked propensity towards procrastination and sloth, 10 lyrical, spherical, diabolical denizens of the deep who all stalled around the corner on the quo of the quay of the quivy all at the same time.
One hen, 2 ducks, 3 squawking geese, 4 Limerick oysters, 5 corpulent porpoises, 6 pairs of Donnell tweezers, 7,000 Macedonians in full battle array, 8 brass monkeys from the ancient sacred crypts of Egypt, 9 apathetic, sympathetic, diabetic old men on roller skates with a marked propensity towards procrastination and sloth, 10 lyrical, spherical, diabolical denizens of the deep who all stand around on the corner of the quay quivery, all at the same time.
One hand, 2 ducks, 3 squawking geese, 4 Limerick oysters, 5 corpulent porpoises, 6 pairs of Donnell tweezers, 7,000 Macedonians in full battle array, 8 brass monkeys from the ancient secret crypts of Egypt, 9 empathetic, sympathetic, diabetic old men on roller skates, with a marked propensity toward participation and sloth, 10 lyrical, spherical, diabolical denizens of the deep, who all stand around on the corner of quay and quay, quivering all at the same time.
One hand, 2 ducks, 3 squawking geese, 4 Limerick oysters, 5 porpoises, 6 tweezers, 7,000 Macedonians in full battle array, 8 brass monkeys, 9 old men, something, procrastination, sloth, 10, blah, 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 blah.
1 hand, 2 ducks, 3 squawking geese, 4 liner oysters, 5 porpoises, 6 tweezers, 7,000 Macedonians in a full battle array, 8 crass monkeys, 9 old men, something procrastination sloth, and 10 blah 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 blah.
Okay, here we go. We have 1 hand, 2 ducks, three oysters, tweezers, something Macedonians, monkeys, brass monkeys, roller skates, spheres, the battle armor, standing at a corner of something and something, quivering.
And that is a lossy transmission line or transfer function. 1 hen, 2 ducks, 3 squawking geese, 4 limerick oysters, et cetera, et cetera, et cetera. Yeah, this is the announcer's test, which NBC used to use for its announcers in the 30s and 40s. And you had to be able to say this with measured tone and memorized. Now, I've been doing this exercise long enough that I've actually gotten it memorized. But yeah, when it comes to actually showing that a lossy signal chain is what happens when you have a big signal chain, you can see that there's actually also interplay between how many different elements there are in the signal chain, but also the complexity of the data being driven through it. So let's go back to the slideshow for a moment here. Just have a couple more slides to this. So as you go through your signal chain, and as it gets longer and as you get more lossy, you generate uncertainty. Now, if I take a certain amount of water and pour it into a glass, look, uncertainty is being generated. That is no longer the same amount of water that I meant to pour into that glass. And so every time that some amount of water sticks to the inside of the thing you're pouring from, et cetera, every time that something spills out, you generate more uncertainty. Well, that was supposed to be exactly 231.2 milliliters. Well, sorry, it ain't anymore. So how do I address that? This is where calibration comes in. I characterize the system, then I adjust it to match a standard, something that I trust. Then I characterize the system again. And this is the cycle that I was talking about before that generates calibration. Do it until it looks right. That's generally the rule. And the reason why I say do it until it looks right is because of the fact that calibration brings down your uncertainty, but pursuing perfection is an imperfect task. It is actually not possible to get something fully, completely calibrated. What you instead need to do is set some particular margin of error, some particular, in mathematical terms, we'd refer to it either as a range or as a manifold, within which you are comfortable saying, I'm close enough. And then when you're close enough, now you've characterized your system, you've adjusted it, you've characterized it again, you're within that butter zone of uncertainty, now you're good. Within calibration, though, the thing is that you also have a cycle insofar as what your dependencies are. You have the standard and you have the device under test. The standard then sets up the device under test to be characterized relative to something that's well known. And, oh, I was wrong. There is one graph. Sorry. So in this case, I've characterized something. I have a device under test, which is an arbitrary unit, and I have a standard, which is an arbitrary unit. You'll see if you go into dev and you see any of my plots that have arbs on an axis, it's because the units are not real. They're just numbers that happen to be there. And after a calibration is done, then you can turn those arbitrary units through this wonderful thing we know as math into real units. But in the meantime, everything's in arbs. So this is a hypothetical transfer function for something that's not exactly dead on, but really, really close. And so the standard is in arbitrary units too on this one. The device under test is on the y-axis because it's the dependent variable in this case. The standard is on the x-axis because that's not going to vary with respect to the device under test. It's only going to vary relative to a quantity or a measurand that we're actually looking at. So when you put the two together, then you get this output. In this case, it's a linear regression of 4 points on this graph that gives us an M value of 0.9949 and a B value of 0.198. Very small offset, even smaller difference from 1 on our coefficient. And also the goodness of fit, the R-squared parameter here, how close all of those points are around the line is also very good, 0.99995. We were actually just going through this in dev, I think it was yesterday, where R-squared is a I'm gonna get in trouble for saying this, but it is a meta parameter. Sorry. Is this the word of the day where I like get ping pong balls dumped on me or something? Yeah, there you go. Just everybody goes wild because it's apparently Pee-wee's Playhouse all over again. Anyway, R-squared is goodness of fit. It's only how close those points are to the line. It doesn't actually tell you anything insofar as the larger number of parameters in the system. It only just says, yes, this line's pretty good. Thing is that R-squared can mislead you if you have a bunch of points that are clustered together somewhere on the line, because then the outliers can wind up weighting the graph less, and the outliers may show you that there's actually noise in with your signal. And we've actually run into that too, where like one area of our graph will look great, and then the rest of it might be just not so good. It'll be a lot more noisy, and that will be the area that we need to improve, generally speaking. That's also something that we see with probes that aren't exactly performing to our spec. They might perform great in a very limited area of the calibration or the characterization that we're doing, but then the probes might not perform well at all at a lower value or at a higher value. And so because we've got a high density of data points in that area where they perform well, the R-squared value is going to look great, but the actual performance sucks. All right, so what about my standards? I have no standards. Well, actually, no, I do have standards, but they're all electronic and they're next to me here. As you go from your measurement instrument, you go up to industrial standards, usually the calibration standards that are used by the manufacturer. Then from there, you go to accredited laboratory standards. So the lab that I worked at was a second-tier accredited lab, meaning that above us were the manufacturer's standards and above them were the national standards. National standards then are at places like NIST, or in the US, or NPL in the UK, or Deutsches Institut für Normung, if I'm pronouncing that correctly, in Germany. I hope I am, but I don't think I am. And then all of that traces back to this little place outside Versailles in France that happens to BIPM, and I'm going to murder this one too, Bureau International Poids et Mètres, which is literally just the International Bureau of Weights and Measures. So yeah, you need to be pretty good at several languages to really work your way through all of this uncertainty and calibration stuff. So to review, here's one big long paragraph that uses every single vocabulary word we looked at the beginning, which is the right way to do it, right? Sensors and actuators are two types of transducers, which are used to interact with the physical world. A sensor, through an instrument that it's attached to, can be used to determine the value of a given measurand through its transfer function, which takes into account the sensitivity of each element of its signal chain. Further, This measurement is done with some given resolution and has a known uncertainty. Once an instrument is characterized, it can be adjusted and characterized again, resulting in what's known as calibration. Finally, the use of calibrated standards to calibrate other instruments results in traceability. So, a discussion that we can have in dev or wherever is, if you'd like to, at some point, choose an instrument or a sensor and figure out what its transfer function is. This is that university-centric idea that I had, because this was the assignment for in class for the kids. But I would urge all of you to actually try it if you'd like. And I'm more than happy to give you a hand if you want to give the exercise a go. Any questions?
That was
I'm trying to think
fabulous.
of, yeah, that was awesome, Pete. Thank you. I'm trying to think
No
of
problem.
what's a weird sensor with an unusual transfer function.
Oh, there are many. I mean, actually,
Yeah.
for us, EC is weird because of the fact that it's our only nonlinear regression that we have to do. That's the one where it's a power law regression instead, and things get way more complicated because of that. Also, it means that when we characterize a bulk of EC probes and module boards, we don't necessarily see all that much overlap by comparison to our more linear sensors. But that's just one. There are many.
Yeah, that's interesting. That's what I was going to ask, is that with 3-point calibration, it's not always a linear
Exactly.
situation that you end up with. That's interesting.
And for that matter, technically speaking, from a mathematical perspective, you actually want to try for 4 points or more, because establishing linearity versus nonlinearity for a function mathematically can't really be done with only 3 points. The thing that we have working in our favor that allows us to do 3 points is that we're working with pretty well characterized sensors from the get-go. And so because of that, because we know what family of functions we should see, then that allows us to get rid of one of those points. If, like I used to have when I was doing calibration for a living, you can run into a situation where you don't know how linear the sensor is actually supposed to be or how linear the instrument is supposed to be, then you need more points to try and figure out which family of functions you should even be barking up the tree of, because there's a whole forest. And finding which one is the right one to look for is sometimes difficult if you don't have enough data to work from. Yeah, I mean, I remember one instance is when you get into polynomial fits and you're looking at something that is a 0th order polynomial, also known as a line, which is the same as linear fit. But then you go to a 2nd order and now it's parabolic. You go to a 3rd order and all of a sudden you got this wiggly cubic function and things just go completely haywire. And then you have 4th order and it's like, wait, that's a parabola, but it's not. And so as you keep going up in order, you'd think that as you have more and more terms, you're getting closer and closer to affining to the actual function you're trying to fit, but you're actually getting further and further afield. So if you ever look at something in Excel and you like keep clicking on the polynomial fit order button where it tells you what the maximum power is, I think Excel tops out at like 6, and you will go through a whole fashion plate of different graphs and functions before you get to that 6th order that look completely different just by what the largest power is.
Hey, Pete,
Anyway.
Pete, can you talk a little bit about why things lose their calibration and how you would know and all that?
Sure. One of the things that's most valuable in not losing calibration is a resistance to environmental variables. And by that, I mean, like, for example, a resistor will change its value due to temperature. Like we were just saying before, I mean, resistivity, length, and cross-sectional area are all temperature dependent. In a thermistor, you're optimizing that resistor to change as much as possible for those variables, for that ultimate measurement or measurand of temperature. In reality, though, every resistor changes with respect to temperature. if you're optimizing for stable design on a board, as Bradley can tell you especially, and as I can tell you from my audio background as well, you try and minimize how much those resistors will vary with temperature. But that's just one way in which calibration can drift. You have something go from one temperature to another, your calibration may not be spot on anymore because the other components on the board will drift. For sensors themselves, we were just talking earlier today about dissolved oxygen sensors. Dissolved oxygen sensors build up a layer of zinc oxide on the inside. And so that's essentially like putting a capacitor in series, well, in a series parallel connection with the voltage source that you're trying to get out of that dissolved oxygen sensor. And it's continuously increasing as time goes by. So you get a bigger and bigger coat of zinc oxide, you get a larger and larger insulator, which means you have less and less signal coming out of the dissolved oxygen probe. And so as time goes by, it drifts. So that's one way in which things go out of calibration as well, is temporal drift. Another way that things go out of calibration is this little thing called gravity. If you drop something that has like a linear trim pot in it, one of those little tiny potentiometers that you have to use a screwdriver to adjust, yeah, banging things around will shift the position of the wiper in that potentiometer. That might change a voltage divider somewhere. That's when I was doing biomedical equipment calibrations, that was by far the thing we most had to actually deal with for calibration, was twisting tiny little trim pots inside and getting them back to where they were supposed to be, putting a dab of Loctite on them and praying that the staff didn't beat the thing up again. So there's all sorts of different ways that you can encounter drift, even right on up to and including like the amount of light on a particular sensor. Like, which one is it? I think ORP probes, I think it is. You can't get too close to a UV source because of the fact that you can actually ionize the surface of the platinum and give yourself a false reading, which is actually true for most ion selective electrode probes, where if you have UV, you get a higher voltage out. If you don't, then you don't. Gas sensors as well drift due to the amount of, well, the gas sensors we're talking about using for FieldKit air, those drift due to the fact that they essentially oxidize whatever gas is coming into them inside of a small, essentially a catalytic converter that happens to be doped with a particular sort of reactant. And the reactant, first of all, gets depleted over a longer period of time. I mean, it's catalytic, so it doesn't actually react as much. But the other thing that happens is you build up carbon inside for like a volatile organic compound sensor. So as that happens, you get more mass, which means you can't transfer as much energy into the gas. You also get less conductivity, or sorry, you get more conductivity because you got this carbon powder sitting inside of the ceramic, conducting electrons through that shouldn't be going through at that point. Anyway, there's a lot of ways that things can go wrong calibration-wise, and the actual remedy for it varies from getting a brush and scrubbing it out to adjusting a trim pot to just doing it mathematically when you can't actually mess with the sensor. I mean, in our case, most of our calibration is mathematical, really. Our calibrations don't actually deal with messing with the sensor directly or altering a trim pot to change some part of a circuit. We're doing math based on what we know for the two measurements between the device under test and the standard, and then we're using that to correct for whatever the error is.
Pete, you said that that we don't need to do like 4-point calibrations because the probes we're working with are already well characterized. What do you mean by that part? Like, that's not a characterization we did to them, right?
No, what I mean is that they are well known in what their sensitivity function or their transfer function looks like. And for the vast majority of them, they're designed to give us a linear output. So because of that, I wouldn't expect to see like a sinusoidal output from a pH probe. I wouldn't expect to see like 0 volts at pH of 7, then at 8, negative something or another, then at 9, positive something or another, et cetera, et cetera, et cetera. So,
and that's based on their construction.
Right. That's based on both the method of their construction and also the information we get from the manufacturer, honestly, just saying this is going to be linear with such and such a coefficient plus or minus some uncertainty.
Is that uncertainty, is that based on the parts they use and the construction, or is it like, and I'm just wondering if like somebody tells you the construction of a pH probe, is that enough to know, okay, 3 points is enough? Or did more go into the probe design and manufacture?
So it's actually back to the theory of operation. So like with pH probes, this is defined by a very specific electrochemical equation, which my brain is not allowing me to recall at the moment. Somebody help me.
E equals MC squared.
No, it's not that.
I'm not going to check it.
Okay. Well, yeah, but we're recording this thing anyway. It hasn't come to me yet, but there is an equation that allows you to, for electrochemical systems, you have a direct proportion between the voltage and a concentration of an ion. pH is a special case where that ion is H plus or H3O plus because hydronium is a thing. And so because of that, because you're measuring what hydrogen concentration is, and so therefore the acidity or basicness or alkalinity, if you will, because y'all not basic, you're welcome. Then that means that the amount of that ion's concentration in the fluid that it's sitting in is going to always give you a proportional voltage. And that simple proportion is what makes it so that we know that it's a linear response. If that simple proportion didn't exist, if it was some sort of weird power law, and by the way, thank you, Sarah. Yes, it is the Nernst equation. Sarah for the win with the chemistry there. So the Nernst equation basically says volts on some particular electrochemical cell, some sort of galvanic cell setup, are equal to some constant times the concentration of the ion you're trying to measure. So because of the Nernst equation, we can say that pH is going to be linear. Because of the Nernst equation, we can also say that ORP is always going to be linear. And then because of the Nernst equation, we can also say that any of the other ion selective electrodes, from like nitrate to ammonium to chloride to, well, I was going to say phosphate, but phosphate levels are usually so low that there doesn't really exist a reliable ISE for them. But any of those, it's just the Nernst equation, so they're all linear. Similarly, with the temperature dependence for resistors, we know that that's a linear function because the resistivity varies directly proportional to temperature as a simple first order thing. That's a linear function. The length expansion that we get and the necking are also both linear, although technically speaking, the necking can be considered to be probably a fractional power or squared, depending on what the cross-sectional area shape is. But in the vast majority of cases, we just treat that as being a full linear function once you've characterized the whole thing. And with something like platinum, where the resistance is pretty low and it's a noble metal that doesn't really want to oxidize, that assumption holds true for the vast majority of cases.
About how big is the speck of platinum in our temperature probe?
It ain't worth it, man. It ain't worth it. I know what you're
curious.
thinking.
Just curious how big. You know how big?
All down and sell the platinum, don't you? I think. I mean, you're in the milligram range, like probably 1 to 10 milligrams. I think it is. It might be slightly more, but either way, it's just this tiny little bit of platinum wire that's got two, I think, copper wires bonded to it. I don't think it's even soldered, or if it is, it's silver soldered.
So it's a cylinder. The cross section's a circle. I
think it's actually rectangular. It's much closer to being like a really, really tiny surface mount resistor, if I remember correctly. But different manufacturers have different form factors. So,
hey Pete, what about the relationship to resolution? Can you talk a little bit about resolution and calibration? Is it always better to have as high a resolution as possible, or what's kind of
there's a balancing act. I mean, this is all engineering problems, and so that means that it's really just accounting. Engineering is the accounting of budgets other than just finance. So the resolution budget that you have for something relies on a number of different factors. One is the noise that you have in a system, and one of the others is the resolution of something like your analog to digital converter, if you're getting that out in a digital fashion. If you're getting it out in an analog fashion, your resolution might be determined by the spacing of the lines on your meter face, for example. But it still comes back to the resolution is dependent both on the uncertainty and then the amount of noise that's throwing the signal into, kind of biasing the signal into one portion of that uncertainty. So that's why we get back to like what I was talking about with effective bit depth versus real bit depth. We have a 24-bit analog to digital converter, but our effective bit depth is closer to 22 bits. Why is that? Because we're losing a few microvolts somewhere in there to uncertainty and noise. That noise can be decreased to a certain extent by lowering temperature, but also as we get lower and lower in frequency, especially of our measurements, we actually increase noise as well. There's this weird hockey stick shaped graph of thermal versus flicker noise, where basically as you get lower and lower in the frequency you're looking at, the noise explodes exponentially. Well, actually, no, it's just 1/f is what it's proportional to. But resolution is defined in this case by how much noise we experience in the everyday conditions we're working within, and then what the range of the analog to digital converter is that we're trying to convert that noise and that signal with. So the bigger the signal is and the further it is out of that noise band, the further away in this case from the 0 volts it is, the better we can measure it up to a certain point. I hope that made sense and answered it. Okay. The other thing I'd point out about resolution is that it is a losing proposition to try to just arbitrarily increase resolution constantly, because of the fact that, well, it runs up against the same problem that you see in quantum physics and Heisenberg's uncertainty principle. The old joke is that the physicist is driving down the road and the cop pulls him over for speeding, and the cop says to the physicist, "So, sir, do you know how fast you're going?" And the physicist says, "No, but I know exactly where I am." And that's the uncertainty. It's a matter of, I can measure one thing, but if that's going to influence another part of my system, then I shouldn't measure it with quite as much tenacity. Similarly with like the probes that we're dealing with, temperature is actually a great example for this. You are always going to be running a small amount of current through a temperature sensor, which does cause it to self-heat a very, very small amount. But if you keep that current low enough, you can keep a large resolution. Unfortunately, it also gets rid of some of your capability of making that measurement to a high resolution, because there's not a very large amount that you can do with no signal whatsoever. So you can't keep a thermistor completely cold, but you also can't keep it with so much current running through it that it heats itself up. Then it will also affect the area around it. In fact, I believe we've had experience with this with the self-heating thermistor 31, or the SHT 31, right? Where this thing actually warms itself up.
Yeah, there's a spec for it. It as you feed the circuit the power that it requires to do the measurement, it's also heating the thing up a little bit. So they suggest certain spans of time between measurements and things like that to keep that from becoming an issue. It's also why, like, if you see our weather sensor board, why there are big cutouts in that board around the sensor, because there are two reasons for that. One is so that the thermal mass of the board itself doesn't cause its temperature to lag behind the temperature of the air. And so that any self-heating can be quickly dissipated because there's a lot of air moving over it.
And also, Bradley, I totally agree that about your comment from the chat that from the EE perspective, basically every circuit is a crappy radio and every lead is a bad antenna once you get up to a certain resolution of voltage. So basically noise takes over once you try to measure really small signals, unless you're really, really careful about the way that you do it. And then you sacrifice money in order to get a signal that may or may not actually be significant.
I mean, there are scientific instruments, especially, I think about things like radio telescopes, where, tiny fractions of a volt are reliably measured. But what that involves is like creating an incredible set of barriers between those instruments and the world of electromagnetic rays that are, spewing in all directions at all times. So like there's a definite floor on what sensitivity buys you in an analog to digital converter, because eventually you're just reading the the radio waves as they come by and you're not seeing signal anymore.
And there's also the converse to that, which is that if you live near the floor of what you can actually do voltage wise, pardon me, usually those more sensitive systems are also more sensitive to interruption by any sort of transients or spikes that you might see. Everything from having a lightning strike relatively nearby to any other sort of electromagnetic phenomenon that gives you a voltage transient or some sort of spike. If it's too sensitive, either you will rail your ADC to one end because you've amplified everything too much, or you might actually damage something within the circuit. That's actually the basis for why EMPs will work on transistor-based devices, because you throw so much energy into a tiny little piece of wire, it doesn't like being anything but a fuse.
Yeah, and I mean, circuits are crappy radios in both directions, which is to say, like, everything that the FieldKit does also, moves electrons around and radiates electromagnetic waves into the environment. So like you can be at a place in the system within FieldKit where you are reading transmissions being made by FieldKit doing its job. So again, we try and drive those down, but on inexpensive field durable circuitry, your options for reducing noise are limited.
Luckily, we have cans.
We do have cans, though I don't suspect they're doing much in that department. We were not able to measure any difference with them on and off. They're mostly just there to reduce the effects of swamp finger and to give us a place to put the sticker.
And Shaw, you were asking about how exactly decalibration occurs. Well, swamp finger is a great example of that, because if you happen to get some water on a trace on one of our module boards in the analog stage, you can accidentally create a resistor that just, messes with things by shunting some current somewhere it shouldn't be and moving it away from the measurement path or the signal chain.
To kind of add on that a little bit, we were in a meeting with someone recently and they asked, like, what are good mechanisms to understand that you've gone out of calibration? And I was just curious, what your thoughts are on using time or some like algorithmic based, like, you need to calibrate because we've sensed this sort of drift or whatever. Like, what do you suspect is like the best way to approach recalibration on? You can talk about our sensors specifically if you'd like, or just anything in general.
Well, from like an international standards perspective, ISO 9000 series and ISO 17025 both specify that the period for calibration should normally be, for most devices, about once per year. And then there are specific subfamilies of devices where it's closer to like 3 months or 6 months. And then there's a whole nother class of devices where it's so incredibly mission critical that calibration needs to be done like daily. In our case, we're probably closer to the 3 to 6 months for most of the stuff and a year for the rest of it. But time-based calibration doesn't actually match up well with our application because we're outside in a variable environment. And you can very well have an extremely constant set of environmental variables for a short period of time, and then swings all over in temperature, humidity, etc. Or you get a little bit of saltwater intrusion into something and things start going haywire. So I think what it comes down to is that knowing what your probes and your measurement system, in our case, I mean the logging system of FieldKit proper, behave like over longer periods of time is where you start learning how to adjust for that. I think that when it comes to seeing if a probe, or like, for example, if we're talking about distance, which I think you probably are, then it's a matter of seeing if you're starting to see excursions, if you're starting to see things that don't return back to what they were initially, then that's a really good sign that there's some sort of offset developing that requires recalibration. Similarly with like pH, if you see a cyclic behavior over time and that cyclic behavior starts to move unilaterally in one particular direction, like if you have a diurnal variance in pH, or if you have like a tide-linked conductivity because you're in an estuarine environment, and all of a sudden one day in July everything offsets itself and you start noticing that, yeah, you know, all of a sudden my salinity's like gone off the charts and it's never come back down, and I'm still seeing the undulations day by day, but there's an offset from the initial base. That's an event usually. That means that like something got stuck to the probe, and so we need to go ahead and clean that off and then recal. So
this is also one of the stupid reasons why many of the early people in the climate skeptic movement were statisticians, because slow, gradual drifts in one direction are red flags for those people. And that this is why. That, you know, by the time that argument was being made, we already had data that suggested that that was not what the problem was, but that was why, one of the reasons why that was their initial reaction to this data set, is like, this should never look like this, which turned out to be true, but not for the reasons that they thought.
Yeah, it's a bit of a thing to try and counter, but also the order of magnitude of time for these drifts to occur that's something that's deterministic. We can characterize that usually. Like and when I come back to things like biofouling, you'll usually see like discrete changes in baseline measurements. So once you start seeing those discrete changes, that's why I was referring to sudden offsets that show up in the data. Those are usually a really good indicator that you need to get that probe out of there, clean it up, recalibrate it.
That was a killer explanation.
That was just a lot of explanation. Yeah, there's that.
Sweet. Thanks, Pete.
No problem. And like I said, you guys have your assignment now.
I'm gonna be thinking about it. I'm gonna come back weeks from now with like a really horrible example.
You can always talk to me via DM.
Yeah. How do we calibrate Jacob? Can we calibrate Jacob?
What is the transfer function?
What's our standard for calibrating Jacob, and what units is the Jacob measure and?
I mean, the most miserable calibration that I used to go through regularly was calibrating stroboscopic tuners, because the confounding variables for generating a precise pitch in air are just gnarly. The temperature of the air, the relative humidity is, it's horrifying. It's horrifying. Everyone gives up. You know, sooner or later, everyone goes down the rabbit hole of, oh, I'm going to calibrate this tuner, and everyone gives up.
Man, yeah. Well, all right.
Yeah. Thanks, everybody. And thank you so much, Pete. And
no problem.
Yeah.
We should definitely do another one of these.
Yeah, I was just going to say.
Yeah.
Yeah,
I have more of these talks up my sleeve too that have already been prepared for other things.